Hello and welcome. In this video, we're going to take a look at another operation with matrices. Now, we've already seen how we can add and subtract matrices and how we can multiply matrices and a few of the restrictions on when we can do those operations. But we haven't talked yet about the division by a matrix. And is that even something that makes sense? So in this video, we're going to take a look at that idea. What does it mean when we talk about division? And it's probably important just to think about real numbers first. When we're dividing by a real number, we're really just multiplying by the reciprocal. So when we multiply by a, if you want to undo that operation, we can multiply by 1 over a, which as an exponent is a to the minus 1. Now keep that kind of idea in mind, because when we want to think about dividing by a matrix, we need to do something similar. We need to find some sort of multiplicative inverse of a. Some way that we can multiply by a matrix and have the multiplication of a and multiplication of its inverse cancel each other out. So keep that idea in mind. Let's take a look at where we would have to have this application. Okay, to see where this idea of having to divide by a matrix comes from, we can take a look at an alternate way to write a system of linear equations. And here I've got 3 equations and 3 unknowns, and we know that we could write this as an augmented matrix. But there's another way that we can also write this equation. If we were just to make a matrix of the coefficients of this particular system of equations, and we take that and multiply by a single column matrix, or a vector, of the variables in this problem, x, y, z, then you can see that by multiplication, on our first row and our column, we will have 2x plus 5y minus z, which is exactly the left-hand side of that first equation. Now, because we can multiply these together, we can say that we'll end up with another 3-by-1 matrix of the 3 equations with the left-hand sides, and we can set that equal to a single column matrix or a single column vector of the 3 constants. And so this has the exact same meaning as our augmented matrix. But the benefit of writing out our system in this form is we end up with a 3-by-3 matrix. We could call that A. We have a 3-by-1 vector, which we could call X. And we have a 3-by-1 column of constants. And you can see we have A times X equals B, which is a very nice and easy looking equation. Now, we want to try to still solve for x, y, and z. In that case, we are actually representing those 3 variables by x here. And we need to figure out, how do we interpret b divided by a? It doesn't really exactly make sense when we're talking about matrices. Division of matrices is not something we know of just yet. But let's compare this to a nice linear equation of the form ax equals b, where a and b are just real numbers and x is a single variable. And that'll give us some idea about what we need to have as being an inverse of a matrix. Now, for any real number a, which is not equal to 0, we can always write a to the minus 1, which we interpret as 1 over a. And this is the multiplicative inverse of a, because if we take a and multiply by a to the minus 1, or if we take a to the minus 1 multiplied by a, we just get the value 1. And 1 is the multiplicative identity. 1 times anything is itself. Now, in a linear equation, when we divide both sides by a, if we have ax equals b, we can actually really think about that as multiplying by this inverse. A inverse times a cancel each other out and leave us with x on the left-hand side of the equation. And as long as we do the same thing to the right-hand side of the equation, we'll end up with a inverse b. And remember, with any kind of equation with real numbers, as long as you multiply the left-hand side and the right-hand side by the same non-zero value, then you haven't changed the meaning of the equation. So this is how we solve a linear equation in a single variable. But now we are going to be taking a look at ax equals b as a matrix equation. And we need to find something that is fairly similar. We need to find a multiplicative inverse of a. To solve a matrix equation ax equals b, the multiplicative inverse of a is going to have the same kind of property as the multiplicative inverse of a real number. We need to have an inverse a to the minus 1, such that a inverse times a or A times A inverse, is equal to the identity. And in this case, we're not talking about the number 1, we're talking about the multiplicative identity, 1s across the main diagonal and 0s everywhere else. Now, it's pretty important just to remember that multiplication of matrices is not commutative. In fact, the only way that this could possibly work is that A must be a square n by n matrix. If A is not a square matrix, then we can't even think about its inverse. Now, how do we go about computing the inverse? Before we calculate the inverse, it's an important thing to note that not every matrix has an inverse. First of all, A has to be square, but even some square matrices don't have inverses. If a matrix has an inverse, then we call it invertible. If a matrix doesn't have an inverse, then we would say it is singular. Okay, now what is the process for finding an inverse? If we have an invertible matrix that is n by n, then what we do is we form a very special augmented matrix that actually has more than one column of constants at the end. We form the augmented matrix that has the matrix A on the left and the n by n identity matrix on the opposite side of the vertical divider. If it's invertible, then through a process of Gauss-Jordan elimination, we will end up with the identity matrix on the left-hand side. In reduced row echelon form, those are all of the leading ones with columns of zeros otherwise. And we'll end up with the inverse of A on the other side of the vertical divider. So let's try that out. We can find the inverse of A through this method, and then we can confirm that it is the inverse of A by the property that A inverse times A and A times A inverse equal the identity matrix. Let's start with the matrix A equals 2, 0, 2, 4, 1, 3, 0, 1, 1, a 3 by 3 matrix. Now, I happen to know that this matrix is invertible. The first step is making sure that we can form the augmented matrix, which is a very easy step of the process. Essentially, we just need to create an augmented matrix that has the 3 by 3 identity on the right-hand side of the augmented line. Now, step 2 is just a single step, but unfortunately, it's a very complicated process. We need to use the Gauss-Jordan elimination method to reduce this to reduced row echelon form. Our goal here is to get the identity matrix on the left-hand side. So, this is a good time for you to try that out, pause the video, and remember, our first goal is to get a pivot position in the top left-hand corner. I'm going to do that here, and you can check your answer. Now, there are two operations that you should have performed to get the first pivot operation completed. Change the 2 to a 1 by dividing by 2, and then make a 0 in the second row. And I've just skipped a step here, and I'm showing what it looks like after the first pivot position has been finished. Now, our next goal is to finish the pivot position in the second row and second column. So you can give that a try. There's only going to be one row operation required here. For our second pivot operation, we just need to take row 3 and subtract row 2 from it. And now you can see that we just have one more pivot position left to go, and that's in the third row, third column. And this is going to take a few row operations. To perform the third pivot, we need to multiply the third row by 1/2, take row 1 and subtract row 3, and take row 2 and add row 3. And this is what it should look like once you've finished all of those operations to get it into reduced row echelon form. Now, what do we have on the right-hand side? Well, on the right-hand side, this green 3 by 3 matrix is a inverse. Now that we have this inverse matrix, now we can solve equations of the form AX equals B for different column vectors of constants B. Okay, suppose that we have the following set of equations. 2x plus 2z equals 4, 4x plus y plus 3z equals -2, and y plus z equals 8. Now, this is equivalent to the matrix equation AX equals B, where A is our matrix 2, 0, 2, 4, 1, 3, 0, 1, 1. X is a column vector of the three unknowns, x, y, and z, and b is also a column vector of the three constants, 2, -4, 8. But because we know that a is invertible, this has the solution x equals a inverse b. So we can just use the inverse of a that we've just found and solve for x, y, and z. X, y, z is going to be equal to the inverse of a times b. And using some matrix multiplication, then we can come up with the solution. And this gives the solution -7, -1, 9. Now the benefit to solving the equation this way using the inverse is simply that we can take the constants vector, in this case 4, -2, and 8, and we can change that to any other three values now, and simply just multiply by a inverse to get the solution directly, as opposed to having to solve a brand new system of equations. Just by knowing the coefficients of all of the variables, if we can find out that that is a matrix that is invertible, then we can simply just plug in different values for the constants and come up with a solution for x, y, z. Now, the inverse is a little bit tricky to compute, and as we've seen, it's not always possible. Sometimes we have a matrix that is singular, and it doesn't have an inverse. But let me show you a very quick way to find the inverse of a 2 by 2 matrix. For a 2 by 2 matrix, let's suppose that A is A, B, C, D. Now, to get the inverse is a very quick shortcut here. A inverse is simply equal to 1 over D times, we swap the main diagonal, D and A, and negate the reverse diagonal, -B and -C, where this constant, D, is called the determinant of A, which is A times D minus B times C. This is the determinant. Now, as you can tell, we're multiplying by a fraction 1 over D. If D is equal to 0, then we don't have the ability to find the inverse. A is singular. Now, a determinant can be computed for higher dimensional matrices, 3 by 3, 5 by 5. It does get a lot more complicated. This formula AD minus BC is only applicable to 2 by 2 matrices. But similarly, if D is equal to 0, then the matrix is singular, even in higher dimensions. So we can do this very quickly if we just choose some sort of matrix that is 2 by 2, where its determinant is non-zero. Here's a matrix B, which is a 2 by 2 matrix, 4, 7, 2, 6. And we can confirm that it's invertible by looking at the determinant. We take the entries in the main diagonal, 4 times 6, and subtract the multiplication of the entries in the reverse diagonal, 7 times 2. So we'll have 24 minus 14, which is equal to 10. Because it's not equal to 0, then we know that B is invertible. The inverse of B is given by 1/10 multiplied by the matrix obtained by reversing the entries in the main diagonal, 6, 4, and negating the entries in the reverse diagonal, -7, -2. And then we distribute the 1/10 in, and we see that we have the inverse, 0.6, -0.7, -0.2, and 0.4. And this can be confirmed to be the inverse by multiplying B and B inverse on both sides. By confirming that they multiply to end up equaling the identity matrix, we can see that B inverse is in fact correct. It's always worthwhile to check this, particularly if we don't have a shortcut for 3 by 3 matrices and we have to use the entire Gauss-Jordan elimination method to find the inverse. It's worthwhile to check your answer by multiplying at the end and ensure that you do end up with the identity. So there we go. Now we have a method for solving a linear equation that is in terms of matrices, a matrix equation. All we need to do is look at A and determine if it is invertible, and if it is, then we can use the multiplication principle of equations by multiplying both sides of the equation by A inverse. And then we just get X, and we solve for X by taking the inverse of A times the column vector of all of the constants. And now this can be applied to any kind of system of linear equations. It's much easier for a computer to do this, obviously. Finding the inverse is a tedious process, but since it can be done through row operations, a computer can compute the inverse very quickly for an invertible matrix. Well, thanks for watching, and I'll see you in the next video.